In probability theory, two events are independent, statistically independent, or stochastically independent if the occurrence of one does not affect the probability of the other. Similarly, two random variables are independent if the realization of one does not affect the probability distribution of the other. The concept of independence extends to dealing with collections of more than two events or random variables, in which case the events are pairwise independent if each pair are independent of each other, and the events are mutually independent if each event is independent of each other combination of events. Definition: for events, two events A and B are independent if and only if their joint probability equals the product of their probabilities. Why this defines independence is made clear by rewriting with conditional probabilities. And similarly, thus, the occurrence of B does not affect the probability of A, and vice versa. Although the derived expressions may seem more intuitive, they are not the preferred definition, as the conditional probabilities may be undefined if P or P are zero. Furthermore, the preferred definition makes clear by symmetry that when A is independent of B, B is also independent of A. More than two events, a finite set of events, I, is pairwise independent if and only if every pair of events is independent, that is, if and only if for all distinct pairs of indices M, K, a finite set of events is mutually independent if and only if every event is independent of any intersection of the other events, that is, if and only if for every n-element subset I. This is called the multiplication rule for independent events. Note that it is not a single condition involving only the product of all the probabilities of all single events, it must hold true for all subset of events. For more than two events, a mutually independent set of events is pairwise independent, but the converse is not necessarily true. For random variables, two random variables x and y are independent if and only if the elements of the pi system generated by them are independent, that is to say, for every a and b, the events x and yb are independent events. That is, x and y with cumulative distribution functions and probability densities and are independent if the combined random variable has a joint cumulative distribution function, or equivalently, if the joint density exists. More than two random variables, a set of random variables is pairwise independent if and only if every pair of random variables is independent. A set of random variables is mutually independent if and only if for any finite subset and any finite sequence of numbers, the events are mutually independent events. The measure theoretically inclined may prefer to substitute events xa for events xa in the above definition, where A is any Borel set. That definition is exactly equivalent to the one above when the values of the random variables are real numbers. It has the advantage of working also for complex-valued random variables or for random variables taking values in any measurable space. Conditional independence. Intuitively, two random variables x and y are conditionally independent given z if once z is known, the value of y does not add any additional information about x. For instance, two measurements x and y of the same underlying quantity z are not independent, but they are conditionally independent given z. The formal definition of conditional independence is based on the idea of conditional distributions. If x, y, and z are discrete random variables, then we define x and y to be conditionally independent given z if for all x, y and z such that p greater than 0. On the other hand, if the random variables are continuous and have a joint probability density function p, then x and y are conditionally independent given z if for all real numbers x, y and z such that pz greater than 0. If x and y are conditionally independent given z, then for any x, y and z with p greater than 0. That is, the conditional distribution for x given y and z is the same as that given z alone. A similar equation holds for the conditional probability density functions in the continuous case. Independence can be seen as a special kind of conditional independence, since probability can be seen as a kind of conditional probability given no events. Independent sigma algebras. The definitions above are both generalized by the following definition of independence for sigma algebras. Let B a probability space and let A and B be two sub-sigma algebras of sigma. A and B are said to be independent if, whenever A and B. Likewise, a finite family of sigma algebras is said to be independent if and only if, and an infinite family of sigma algebras is said to be independent if all its finite subfamilies are independent. The new definition relates to the previous ones very directly. Two events are independent if and only if the sigma algebras that they generate are independent. The sigma algebra generated by an event E sigma is, by definition, two random variables x and y defined over omega are independent if and only if the sigma algebras that they generate are independent. The sigma algebra generated by a random variable x taking values in some measurable space S consists, by definition, of all subsets of omega of the form x minus 1, where U is any measurable subset of S. Using this definition, it is easy to show that if x and y are random variables and y is constant, then x and y are independent. Since the sigma algebra generated by a constant random variable is the trivial sigma algebra, omega, probability zero events cannot affect independence, so independence also holds if y is only p are almost surely constant. Properties. Self-independence. Note that an event is independent of itself if and only if. Thus an event is independent of itself if and only if it almost surely occurs or its complement almost surely occurs. For example, if A is choosing any number but 0.5 from a uniform distribution on the unit interval, A is independent of itself, even though, tautologically, A fully determines A. Expectation and covariance. If x and y are independent, then the expectation operator E has the property and the covariance cov is 0. Since we have characteristic function two random variables x and y are independent if and only if the characteristic function of the random vector satisfies in particular the characteristic function of their sum is the product of their marginal characteristic functions, though the reverse implication is not true. Random variables that satisfy the latter condition are called sub-independent. Examples: rolling a die. The event of getting a 6 the first time a die is rolled and the event of getting a 6 the second time are independent. By contrast, the event of getting a 6 the first time a die is rolled and the event that the sum of the numbers seen on the first and second trials is 8 are not independent. Drawing cards. If two cards are drawn with replacement from a deck of cards, the event of drawing a red card on the first trial and that of drawing a red card on the second trial are independent. By contrast, if two cards are drawn without replacement from a deck of cards, the event of drawing a red card on the first trial and that of drawing a red card on the second trial are again not independent. Pairwise and mutual independence. Consider the two probability spaces shown. In both cases, p equals 1/2 and p equals 1/4. The first space is pairwise independent but not mutually independent. The second space is both pairwise independent and mutually independent. To illustrate the difference, consider conditioning on two events. In the pairwise independent case, although any one event is independent of each of the other two individually, it is not independent of the intersection of the other two. In the mutually independent case, however, mutual independence. See for a three-event example in which and yet no two of the three events are pairwise independent. This example shows that mutual independence involves requirements on the products of probabilities of all combinations of events, not just the single events as in this example.